Okay, this video is going to be looking at calculating the standard Gibbs energy or the Gibbs free energy of a reaction. This starts on page 913 in your textbook. There are two basic methods that we can use to calculate the standard Gibbs energy of reaction. So the first method, for looking to calculate delta G naught of reaction, is using our formula for the Gibbs energy, which is delta H naught of reaction minus T delta S for the reaction. And what we do with these is we can calculate the standard enthalpy of reaction by looking up these enthalpy values in the back of the textbook. And this looks like the sum of the molar coefficients times the standard enthalpy of formation for the products minus the sum of the molar coefficients times the standard enthalpy of formation for the reactants. And similarly, we look up these values, and standard entropy change for this reaction would be equal to the sum times the molar coefficients of the entropy of formation. We just call it entropy. The entropy of the products minus the sum, that was terrible, minus the sum times the molar coefficients of the standard entropy of the reactants. So that's the first method. It involves two longer calculations of calculating the standard enthalpy, delta H naught, and then delta S naught, and plugging in T. And we're going to do that in example down below, example 20.4 from your text. The second way is a little bit more straightforward, where some of this legwork has been done for us, so we can calculate the delta G naught of reaction, which is just going to be the sum of the molar coefficients times the standard Gibbs energy of formation for the products minus the sum times the molar coefficient of the standard Gibbs energy of formation for the reactants. So in the second case, we're essentially doing the delta H naught of reaction and the delta S naught of reaction, but it's already been done for us. It's just a delta G value that's listed in the textbook. And I will show you an example of that for example 20.5 at the end of this video. So we'll do these two examples here and kind of demonstrate both of these processes. And we'll use the same reaction to make sure we get the same result both times. So the first one's example 20.4. This involves a reaction between potassium chlorate as a solid, and we're going to heat this up, and it's going to undergo a disproportionation reaction, and I'll explain that here in a second, to become potassium perchlorate and some potassium chloride. Now, a disproportionation reaction is a type of redox reaction which we haven't gotten to talk about, where we have one reactant that undergoes both a reduction and an oxidation on itself. So it's disproportionating into two products that have different oxidation states. So the chlorine in the perchlorate is +7, and the chlorine in the potassium chloride is -1. So it's gone from +5 to +7 and -1. That's just a specific type of reaction. This reaction is used a lot in fireworks and also in match heads. And it's an example of a spontaneous reaction where, again, once you've provided the activation energy, it will continue forward until it runs out of the reactant potassium chlorate. So they'll put potassium chlorate in a match head, and if you heat that up by striking it along the box, this will continue burning and undergoing this redox reaction to produce these two products until that match head is all used up, or at least the chemicals on the tip of the match head are used up. So what I like to do is just list out my values that I'm going to need from the back of the text. Kind of makes things a lot easier. So the standard enthalpy of formation for the chlorate is -397.7 kilojoules per mole, and for the perchlorate it's -432.75 kilojoules per mole, and the chloride, potassium chloride, is negative 436.7 kilojoules per mole. And again, you just look these up in the back of the text. And the standard entropy of each of these is 143.1 joules per mole Kelvin. So you got to be careful with that kilojoules versus joules difference. 151.0 joules per mole Kelvin. And 82.6 joules per mole Kelvin. And again, we're doing this is all listed under standard conditions, so that would be normally at 25 degrees Celsius, which is 298.15 Kelvin. And that'll come back important at the end of the problem when we start plugging all this into our original equation of delta H naught reaction minus T delta S. So the first thing we're going to do is calculate delta H naught of reaction. So this becomes the sum, as we've shown below. I'm not going to rewrite that because it takes up a little too much time. So it's just the sum of the products minus reactants for the standard enthalpy. So looking up here, my reactant for the perchlorate, it's going to be 3 moles times the negative 432.75 kilojoules per mole plus 1 times the negative 436.7 kilojoules per mole. And that's all going to be minus the reactants, which was 4 times negative 397.7 kilojoules per mole. And kind of combining some terms within the brackets here, we would get delta H naught of reaction is equal to negative 1734.95. And now it's just kilojoules because we multiplied it by the molar coefficients, so the moles drops out, and minus negative 1590.8 kilojoules. One more step of combining those together, and I get the standard enthalpy of reaction for this reaction is negative 144.2 kilojoules. Let's put a box around that. We're going to need it here in a little bit. And the next step is we're going to calculate the standard entropy change for this reaction, which looks very similar. It's the same type of problem where we're going to use the molar coefficients times the standard entropies of each of these. So again, this becomes 3 times 151.0 joules per mole Kelvin plus 1 times 82.6 joules per mole Kelvin minus 4 times the 143.1 joules per mole Kelvin. Again, combining terms, delta S naught of reaction is 535.6 joules per Kelvin. Again, the moles go away because we've multiplied it by the molar coefficients. And that becomes minus 572.4 joules per Kelvin. So our final answer, the standard entropy of reaction, is negative 36.8. So negative 36.8 joules per Kelvin. I'm going to leave that in joules per Kelvin. At the very end here, we're going to convert it. So finally, to calculate delta G naught of reaction, it's delta H naught of reaction that we calculated earlier minus T times delta S naught of reaction that we just calculated. So delta G naught of reaction is equal to negative 144.2 kilojoules, as we calculated earlier, minus our 298.15 Kelvin times the negative 36.8 joules per Kelvin, but we also need to convert joules into kilojoules, so for every 1 kilojoule there is 1,000 joules. Let's just go through and double check our units canceling out. Joules cancels joules, Kelvin cancels Kelvin, so we'll get an answer in kilojoules. This becomes negative 144.2 kilojoules plus, let's be consistent here, minus a negative 10.97 kilojoules. So that's the product of 298.15 times negative 36.8 divided by 1,000. And finally, we get delta G naught of reaction is equal to negative 133.2 kilojoules. So Gibbs energy values are typically listed in kilojoules, and as we can see, this is negative, so that means it's spontaneous, and it's a very negative number, so this reaction will really go towards the products. It has a lot of energy available for this reaction, so it likes to go forward. The second part of this is example 20.5, and we're going to be doing the same process, but this is a little less cumbersome to go this way because we just look up the Gibbs energy of the products and the reactants to find out the change in Gibbs energy for the reaction. So let's just rewrite this reaction really quickly. For KClO3, three moles of KClO4 and potassium chloride. And now we go in the back of the textbook and look up. These are all listed in the same table as well in the back. This is negative 296.3 kilojoules per mole. This is negative 303.2 kilojoules per mole. And this is negative 409.2 kilojoules per mole. So again, all the work here in calculating these has been done for us, calculating the delta H and the delta S. So we're going to use the second formula up there, which is the change here is going to be the, let's just rewrite this one really quick. Standard energy change of Gibbs energy is going to be the sum of the molar coefficients times the standard Gibbs energy of formation for the products minus the sum times the molar coefficients of the standard Gibbs energy of formation of the reactants. So again, this just becomes delta G naught reaction is equal to the 3 moles times the negative 303.2 kilojoules per mole plus 1 mole times negative 409.2 kilojoules per mole minus, close that bracket, open another one, minus the 4 moles times negative 296.3 kilojoules per mole. Again, combining terms, delta G naught of reaction. The left side here becomes negative 1318.8 kilojoules. Again, moles are canceled out. Minus a negative 1185.2 kilojoules. And all of this simplifies down to a standard Gibbs energy of reaction of negative 134 kilojoules, which if we compare it to the value we got previously, those are pretty darn similar. The only difference would be maybe some rounding or some different values that they put in the textbook. So those are the two different ways we can calculate the standard Gibbs energy change of the reaction.